And just to prove it to you, this is the function for a 1s, this is the function for a 2s. You see they're different functions which are based on a radial and an angular component. That's not too important. I don't want to get stuck into the quantum mechanics of this. If you want to do this stuff, you can take a quantum mechanics course, but basically that's where I think it's important to explain to students that's where the orbitals come from, because I think very often, you know, if you take a course in chemistry to say, here's an s orbital, here's a p orbital, this is what they look like. Where does that come from? It comes from this. And it comes from plotting this as a probability in three-dimensional space, and then translating that to a boundary surface. Yes?
So, where do they sort of sit in relation to each other? Are they all inside the other one?
Correct.
And with the probability diagram on the 3s, the circles inside aren't the other two orbitals?
No.
They're also part of the 3s orbital?
Correct.
Okay.
Right, these are distinctly different because these are distinctly different functions.
And if you have a 4s, would we have like 4 layers?
Correct.
Okay.
Correct. And 5s would be 5 layers.
Okay.
It's very cute. Okay. All right. So I think this is really cool. I mean, all right. Now let's. So that's the story for S. What about P? So things get more complicated. So if we look at the P subshell type again, if we take, basically we're doing the same thing. We take the Schrödinger equation, we find a solution which is a wave function psi, which will be something very mathematical that looks like this with a radial and an angular component. We plot this in three-dimensional space and we get something that looks like this. Translated, it will look like that as a probability distribution, and to make our life simple, we draw it as a sort of a closed dumbbell-shaped thing. And because we have 3 p orbitals, there are 3 of them, px, py, and pz, and that's sort of what they look like projected onto the Cartesian axes. Like they look like they have a dumbbell shape. Now remember, there's 3 of them. Why are there 3 p orbitals? Why are there 3 and not 6 or 3 or 4 or 2? What's the reason?
The magnetic moment.
Not magnetic
L.
moment. L. Orbital angular momentum quantum number for a p subshell type is what? 1.
0, 1. So we have like
3, correct. So the L value is 1. There are 3 possible ML values, and the ML values, now you see it sort of in pictures, I said to you, reflects the orientation of the subshell type in space, and here you see it. Okay. Now for D, it's the same. We have the same thing. Here we've got 5 orbitals. I do expect you to know S, P, and D, right? I don't expect you to know F. I'll just show that to you in a minute. But there's 5 d orbitals. This is their shape. They've got different colors because they've got different phases, right? Phases come from basically the mathematics associated with a wave function, psi, if it's plus or minus. Don't worry too much about that, but basically you have a plus phase and a minus phase, which comes from the mathematical form of the function that makes up these things. You also see that we have something called the nodal plane, which is shown here for one of these orbitals. In fact, there's 2 nodal planes for these 4 orbitals. A nodal plane is a plane where there's absolutely no, for that orbital, no electron density. Okay, we call that a nodal plane. Now these orbitals, d orbitals, are very, very important in my field, which is inorganic chemistry. In fact, it's all about d orbitals. The chemistry of the transition metals is dictated by these guys here. But for organic chemistry, which is the chemistry of carbon, S and P is typically, enough, because of course carbon doesn't have d orbitals. And if you really want to see some interesting orbitals, these are the shapes of the f orbitals, right? There are 7 of them. And you can see as we get to higher angular momentum quantum numbers, the forms of these orbitals become more and more complex, as is depicted here. I don't expect you to know the f orbitals. I do expect you to know and be able to draw s, p, and d, right? Because I think those are important. And be able to know what the difference is between, let's say, a dxy and a dyz orbital, or a dz squared orbital. So I do expect you to know that. I will not expect you to draw the f orbitals. Okay, but this I just show you for your own interest. I show you here without the phases, but this is what they look like. these orbitals are very important in F-block chemistry, right? The lanthanides and the actinides. So if you want to do some really exciting chemistry, I've done some of this myself. The elements right at the bottom of the periodic table, like samarium and gadolinium and europium and uranium, the chemistry there is dictated by these guys. That's why it's called the F-block elements, because the electrons are located in the F orbitals, yes.
So like, I see like the bottom ones that have like 7 orbitals, but like the top ones there, I see the ring and I know that's like around the balloon, those ring things. I know that's an orbital, but
it's not an orbital. This whole thing is an orbital.
Or they're the electron things, but I see there's only 4 of them, so it's just like 2 rings and 2 balloons.
So what? Well, the point is, here's the point. The point is that each of these that's one orbital, that's an orbital. So there's 7 of them, and each of these things, regardless of the complexity of the shape, it's a good question. Each of these things can accommodate 2 electrons only. Now that's weird, but this can accommodate 2 electrons, so can this, right? So these are distinct orbitals.
So,
okay. Yes.
So an atom is composed of, because this was for me difficult to understand. But so an atom is composed of S, D, and F, not just F or just S.
Oh, all of them.
Yeah, exactly.
All of them. Yes. You don't just have. It comes from the structure of the energy levels. Yes.
How do they compare to each other in terms of size? Like the F orbitals huge compared to the S orbitals, or?
It's a very good question and a very difficult one to answer. It depends on which energy level you're in. Okay. So, for example, in the lower energy levels, the S and the P are the same size. Okay. But if you get to higher energy levels, there's a big difference in the size between the S and the P. That's a very interesting question, and it has very interesting consequences for bonding in heavier elements, because there's a big mismatch in the orbital size. For lower energy levels, the size is the same. For higher energy levels, there's a big difference in the size between S, P, and D. That's the answer. Okay, so now we've now looked at the orbitals. Now let's look at something called the Aufbau principle. So how do we fill up the electrons in the atom? We don't just sort of haphazardly throw them in. We've drawn now the structure, the architecture, via the energy levels, and we've given it some structure. Now let's put the electrons into those orbitals. How does that work? Well, it follows something called the Aufbau principle. And who of you can speak German? Right, so what does Aufbau mean?
Construction.
Sorry? To build something, yeah, to build something up, right? Aufzubauen. The way that this goes is what this diagram shows here. It's actually very simple. This is the order, and this has been experimentally determined by which the atom is filled with electrons, right? First 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, and so on. Notice what happens when we get to the 3rd energy level. Now, one would intuitively think that you'd first fill up the 1st energy level, then the 2nd, and then the 3rd, and then the 4th. But it turns out that when we get to 2p, check this out, we first fill 4s, then 3d, and then things sort of get completely muddled here. Now, the reason for that is simply that it's been experimentally determined the energies of these different subshell types, and it's been shown, for example, that a 4s orbital is lower in energy than a 3d orbital. That's why it gets filled first, although it has a higher principal quantum number, and in fact exists in a higher energy shell. That sounds counterintuitive, but it's not really. It's just a matter of energy.
2 questions. First question about the 3D. Might it be like, because the 3D orbital has just more electrons in it, that need more energy?
No, not really, because remember, each orbital can only accommodate 2 electrons anyway. Oh, you're saying there's more of them, so that's...
Yeah, because you have like 5 shells in the 3D and just 2 in the 1 in the 4S, so that might be just a question.
Well, that's an interesting speculation. I mean, I don't know if that's the reason why the energies are different. The fact is they are different. That may be the case. I suspect it's not though, because if that were true, then the 2p orbital would be would also, there would be a problem with a p2 because there's 3 of them. So I don't think that's the reason. I think it's just a factor of having you know, different. It's just a pragmatic matter of fact that if you go and you measure the energies of these orbitals, that it turns out that that's the order in which they lie.
Is, for example, the 3D layer like further away of the nucleus than a 4s?
Interesting question. Very interesting question. We have 2 issues. We have distance and we have energy. So the energy, the distance is the distance of the 4s is further away, but the energy is lower.
Why? Wouldn't it be like the closer the higher side potential energy?
That's what you would expect intuitively. Again, I said that this is kind of counterintuitive, that you have things swapping around. But it's again because if you measure the energies, that you find that this is the reason why. But let's go on and have a look at this just a second. This is sort of the overall picture, right? So you can see for n equals 1, everything's fine. N equals 2, S and P. And notice that if I fill up the electrons, each orbital gets 2 electrons, right? You see that? Spin up and spin down. I denote that with an arrow pointing up and an arrow pointing down. And this is where things start getting muddled. S, P, and D. So this is, you see, the energy is lower. The energy of the 4s is lower, but it's in fact further away from the nucleus because it's in a higher energy level. So I know that sounds weird, but quantum mechanics is weird. Okay, and it really is, right? Could spend an hour talking about that, yes.
So if I remember correctly, the dip in the energy level usually happens around, in terms of periodic table, happens around the natural earth metals, right? Am I correct?
What do you mean?
Like whenever you plot out the SPDF orbitals on a periodic table,
Right.
that weird dip with the D, that happens around with the natural earth metals, right?
Well, I don't really know what you mean, the dip in the energies, but maybe we can discuss that later.
I think it's like the letter to where, like, you know, some of the like a 4s is a lower energy than 3d.
Oh,
the
I think
atomic
a
number.
4s would be like a metal going from like.
Well, I mean, the point is that this is just this is always the case, right? It's not just for specific elements. It's always the case.
Yeah.
Always. So this is the structure of how you fill it up. We call this the Aufbau principle, and you can either draw it as a diagram, as I've drawn it here. Remember, the y-axis is energy, and or you can just write it out as the electron configuration. Now, this is sort of how we fill it up, right? Using this diagram here as a guideline, I would recommend that you write this down so that you don't get confused. Yes.
Yeah, that's my question actually from before. So we have to write it down in this energy because we at the University of Bonn they told me like we can have the linear.
Don't worry, we're going to get to that in a minute. You're talking about writing it down as an event. Yes. Just give me a moment. I'm getting.
Okay.
So this is just to help you denote the order of filling. This is just the so-called Aufbau diagram showing the energies. You can draw it, or you can write it out. We're going to get to that in a second. Now, before we get to that, I just want to highlight 2 further rules: the so-called Pauli exclusion principle and Wundt's rule. Now, there were all these German scientists doing this. So Pauli was one of them, and he was quite a big guy, and he came up with this idea that every orbital can only have 2 electrons, and only 2, right? That's called the Pauli exclusion principle. Another way of phrasing it, sort of more formally, is that no 2 electrons can have the same set of quantum numbers, right? Because there's 4 quantum numbers. In other words, an orbital can only have 2 electrons spin up and spin down. That's the Pauli exclusion principle. Wundt's rule is also called the rule of maximum spin multiplicity. And what it basically means is as we're filling up p or d orbitals, each p orbital will first get one electron before you fill up the second one. So let's suppose I've got four electrons that I want to distribute into a p orbital, right? This is the Hund's rule of maximum spin multiplicity. Just to illustrate it, if I've got p, let's say 2p, and I want to put 4 electrons into these orbitals, well, I can do it like this, or I can do it like this. And Hund's rule says that you do it like that. Right? That each p orbital first gets 1 electron before the second gets an electron. And the reason why is maximum spin multiplicity, or maximum spin. It turns out that atoms want to have a higher spin value. That's why each orbital first gets 1 electron, because each electron has a spin, and if they're paired, there's no spin. Right? Because remember, electrons are like little magnets. That's a very simple description of why we have Hund's rule. Yes?
Oh, what is the experiment behind this discovery that atoms want a higher spin number?
Well, the experiment, well, I don't really know what experiment Hund's actually did. I don't think if he actually did it, he was a theoretician, as far as I know, but, they found out that if you, the way that you can find it out is if you take an atom, you can actually figure out what the electron configuration is experimentally, right? So if you take an atom like, I don't know, boron or something, and you do atomic absorption spectroscopy, you can figure out, or some other type of spectroscopy, you can figure out what the electron configuration is experimentally, which orbitals have which electrons, and that's how they figured it out, right? So but we have to move on, right? Because we've still got really a mountain to get through. So for the moment, write down your questions, and if there's time at the end, I can answer them, okay? Now, this is the way that we can represent it. We saw it via an Aufbau diagram with energy, but we can also represent it like this. This is the electron configuration for the first couple of elements, right? The first, 11 elements. And you can see basically how this goes. S, you first fill the 1s and the 2s and the 2p, and here I've just drawn a 2px, 2py, 2pz, and so on. Now to get back to your question, you can either draw it like this. This is also sort of an Aufbau diagram in a way, just not drawn in terms of energy. This would also sort of qualify as an Aufbau diagram. Or you could write it out, the electron configuration, okay, which is much more convenient. So you can write out the electron configuration for hydrogen would be 1s superscript 1, meaning that there's 1 electron in that orbital. So this is what you'd okay, well, before we get to that, maybe we should just look at how we can write this down. So let's take boron, for example. You see that there is the Aufbau diagram for it over there. And if I were to write that out, its electron configuration would be this. So you can write it out. 1s2, 2s2, 2p1. What about oxygen? Oxygen would be 1s2, 2s2, and then 2p. How many electrons do we have there? 4. Okay? And so on. So that's the way to do it. You can either draw it or you can write it out. And this is the electron configuration. Now, there's a shorthand notation called noble gas configuration. So noble gas configuration is basically, again, just to make our life simpler. For example, if we take lithium, the electron configuration is 1s2, 2s1, and this is sort of a shorthand notation of it, where in square brackets you put the noble gas helium, which tells you that the electron configuration is essentially the electron configuration of helium plus the 2s1, okay? Sodium, just to give you another example of noble gas notation for writing down electron configurations. 1s2, 2s2, 2p6, 3s1 is the electron configuration. Noble gas notation would be square brackets Ne, 3s1, because the electron configuration of neon is 1s2, 2s2, 2p6. That's a shorthand notation, which you can use, right, to save time. So there's two ways of representing it summarized. We can represent it as an Aufbau diagram in terms of energies, or we can just write it down in terms of electron configurations as I've done here. And you can use noble gas notation as I have depicted here. So don't forget that. Now let's just look at some deviations. Previous years I didn't teach this. I've decided this year to throw it into the course. There are some deviations from this Aufbau principle, where we have that triangle that we drew to fill up the electrons in the transition metals. So what I have here is the electron configuration of the so-called transition metals. Okay, not all of them, just the 3D ones, the ones at the top of the transition metal series, the elements in the middle, the metals. And you can see that this is the electron configuration. Now this all follows the Aufbau principle that we just had earlier. You see, you first fill the 4s and then the 3d, right, in each of these cases. By the way, they're called the transition metals because it's a transition from an empty to a full d orbital. So you know, as you fill those d orbitals, it's sort of a transition. But that's one way of looking at it. Now, there are two exceptions to this. The two exceptions, chromium and copper. Now look at the electron configuration of chromium. Right, you see, this is nice because that's sort of the Aufbau representation, and that's the electron configuration. I hope that answers your question. Right? There's two ways of representing it. Now what is going on there? What's strange there?
It doesn't respect like the Hund principle.
Correct.
Because the 4s is like filled up.
Correct. It doesn't respect. I like that. So it's being disrespectful to the Aufbau principle. Okay. And what about copper? What's strange there? Same thing. It doesn't respect the Aufbau principle.